Hello, everybody. I'm Frank Roschmeyer, and it's my pleasure to speak here today. I'm with ETAS since 2013, and I worked in Germany, but also 5 years in China. And now, since beginning of this year, I'm product manager for ETAS Cloud Services Model Simulator with a focus on Asia regions and our virtual networks. So with ETAS, our target is to empower tomorrow's automotive software, and we drive the software-defined vehicle forward. And today I will give you some deeper insights into the development tool chains, and here for the product field test topics. So our target at ETAS is to enable IT topics into the automotive industry. And from the IT area, we know that 3 major KPIs are driving the software development, which are now accepted by the automotive industry, namely deployment frequency, lead time for changes, mean time to repair. And we made some research, and the research clearly stated that high performers in these areas had 50% higher market capitalization growth compared to low performers. And high performers are twice as likely to exceed organizational performance. So our target at ETAS is to move you to the elite state if you're not there already. And today I will provide some insights into fuzzing technologies that we have established at ETAS, which can help you to move into this elite area. Before we go into details of our fuzzing solution, I would like to quickly give an overview about our solution that we currently offer, which is related to DevOps, of course, starting on the left side with the virtual desktop on which you can set up your development tools, configure and code generate, set up software component integration, build artifacts like virtual ECUs, for example, combine it and integrate it with plant models or configure it, and then apply scenarios on this virtual vehicle setup. Then you can execute this either on a PC in a software in the loop mode, or you can scale it up in our ETAS Cloud Services model simulator setup. And at the end of this chain, you can apply some analytics on the output, get some reports out of it, and go back to the beginning of the development phase and update your software. I will focus today on one part here that's called a virtual validation fuzzing. This is a relatively new topic for the virtual testing, but it's already but we have an established tool which is called CycurFUZZ from our security colleagues, which is already in the field proven as an outstanding tool. I will touch topics on DevSecOps and also some legal topics which have a big impact here on the solution. Our holistic solution view is that we provide managed services like fuzz testing, and if we zoom into the test part of the DevOps circle, our target is to move from the right side, from manual tests, as many tests to the left side to enable you to automate those tests and gain a lot of efficiency and improvements on optimization. And the target here is, of course, to improve the quality of your software, networks, and the robustness. But first, let me come to DevSecOps. So where does that actually come from and who is an important contributor to this approach. I found this reference here from the Department of Defense. And they say the main characteristic of DevSecOps is to automate, monitor, and apply security at all phases of the software lifecycle. So not only at the end of the software development, not at when it's delivered to a vehicle, for example, but continuously with the development of the software function. Security needs to have a very important role in that. And of course, testing, automized testing, is here also a key differentiator. Now let's come to a holistic solution view. So nowadays we talk a lot about the software-defined vehicle and about the advantages of the software-defined vehicle of decoupled hardware and software. And in the future, there will come, of course, a lot of more software to the vehicle. And if more software comes to the vehicle, of course, that also has implications on cybersecurity risks, which most probably will increase. New legislations, so having the acceptance at the end for the type approval of your model. There are some very important legislations coming up, and I just picked out some pieces of those legislations which are of importance, especially in the direction of testing. So the OEM has to have appropriate and sufficient testing to verify the effectiveness of the security measures implemented. So it has to be proven that the OEM has implemented those measures and has this testing done and under control. And what is very important, also considering the DevOps cycle and also considering that a lot of software functions will be released after the SOP, it is very important that there is a pre and post SOP testing capability set up. And on several passages in those legislations, fuzzing is strongly recommended and seen as one of important parts of testing. And regarding the legislation, unfortunately, it's also a moving target. We just had an update in May this year, which also emphasizes the testing part. SecOps, DevSecOps, I already mentioned. So within the development, starting with the first lines of codes, it's always important to have security in the mind and also to automate testing, to test this huge amount of software, which is more interlinked to each other. And the potential business impact if customers are not reacting to those topics is exploding costs. How is it done today? So nowadays, huge groups of developers and testers are writing tests, pushing those tests to a test server, set up and analyze the outcome of those tests applied to ECUs, maybe even hardware ECUs, and usually closely before the end of the SOP, there might be some occasional security tests. Of course, there are a lot of risks in this approach. Therefore, for the tomorrow setup, it will be fully automated. It will be most probably in the cloud. A lot of tests are continuously running, many security tests and tests as a service. What it will do, it will increase efficiency. It will avoid exploding costs. You will be faster to the market. Just remember those 3 metrics I mentioned before. You will accelerate on all 3 of them. You will find bugs much earlier in the development phase. And if you find them earlier, of course, they are cheaper to solve. It will also increase the effectiveness. It will increase the test coverage, the detection rate, and you will find bugs much more effective. fuzzing, on what we at ETAS have here to offer. Fuzzing, if you look into the media, sometimes is seen as the hacker's bug scanner or an automated software robustness test method, and it's pretty much established in the standard IT industry, and we will introduce that to the automotive industry. And for that, of course, there are some adaptations needed for protocol testing. For example, it has to be applied on our well-known automotive buses, CAN, LIN, Ethernet, FlexRay, etc. The principle, I will have another slide for that. I will show you later on what the principle is of fuzzing, and the overall solution will be a managed cloud service, a cloud service that can be fully automated, adapted to automotive use cases. It will be simply deployable, and it needs to be modular and scalable so that it can also be easily automated. Now I will give you some intro about what we have. And before that, I would like to give you a short recap about what fuzzing is. So if you look here into this area here, this light blue area framed with a green frame, this is where some valid input comes into the ECU software or function. Yeah, and on this valid input, there will be a defined behavior which is accepted. A fuzzer will apply to the target, will test the target's reaction to randomly generated invalid or unexpected input. And it will be applied also on these software functions or on the full ECU. And the target here is to improve the robustness of the network or of the software. Invalid input should lead to some rejection. So it should not lead to a disastrous behavior of the software or the ECU. That's the wanted reaction. But there will be also some unexpected input, which is maybe not covered by the software, or not solved by the software, or even it's a bug, or it could be a security vulnerability. So it finds the way into the system, into the software, and here it can lead to undefined behavior. It can be some insecure behavior, so like data leakages, memory leakage, or it can lead to some undefined behavior. And in the worst cases, it can, in the vehicle, of course, lead to some crashes, and will have significant impact on the passengers, on the brand of the OEM, etc., etc. There are different types of fuzzing, usually differentiated between primitive, dumb, and smart fuzzing, white box and black box fuzzing, And within ETAS, we have a solution. It's called ETAS CycurFUZZ. It's a protocol fuzzer, which can be applied on the well-known automotive networks. Here you see the graphical user interface of that tool. It is already used in customer projects many years on hardware, but also on software in the loop targets. At the end, if a fuzz job is done, you get a report out of this tool, and in this report you can see that the ECU didn't respond, or it didn't respond in time, which could be also an indicator that it crashed, for example, or that something unexpected happened at the ECU or ECU software. And with this report, you can also take those cases where the software had an undefined behavior, and you can replay those cases when you adapted your software, and to see if those use cases where it failed before, if it had been solved afterwards. So a very powerful tool that enables you to increase your network and software robustness. And it enables you also to find some security vulnerabilities. We did a benchmark with a well-known competitor's product. We applied it on the same target, and we did several benchmarks. And the first benchmark is about failures found, so the numbers of failures found in this fuzz run, which took with our product around 17 hours and with the competitor's product 23 hours. And you can see CycurFUZZ could find many more failures. CycurFUZZ was also much faster. Here you can see on the y-axis that's the average number of test cases per second. And we could also find a lot of defects. Here in this case, 8 defects, and the competitor product didn't find any defect. Here I brought with me some examples of fuzz test findings that we had. It's just an extract of it. There are, of course, many, many more. I brought those with me just to give you an impression. So we did some fuzzing on the gateway ECU, and the controller stayed in the bootloader. And yeah, you can imagine that's quite a bad situation here. We also managed to apply fuzzing, and that the ECU stopped responding. And it didn't only stop responding, you couldn't easily restart it. So what we had to do was power disconnect, reconnect, and then the gateway ECU rebooted. We also could crash devices. Also here, power on cycle was needed. Another crash via Ethernet fuzzing on the instrument cluster. Then we could also force a radio reset via Bluetooth, and also create a loose Bluetooth functionality. And that might, of course, have some impact on the user experience of the customer. Just imagine nowadays, if you open your vehicle, maybe with a smartphone, keyless use cases, that would lead here most probably to a situation where your customer cannot open the vehicle. So here just some examples of our findings with CycurFUZZ. And now I will move on to CycurFUZZ for software in the loop and cloud execution. Here, this overview, I will give a quick introduction to that. I will start here on the left side with our ETAS simulation middleware, which is called COSIM. It's an integration platform which enables you to connect different kinds of FMUs, for example, plant models, but also to implement virtual ECUs, which have been created, for example, with our ETAS vECU builder. And then you can connect those virtual ECUs on a virtual level with our product ETAS vNet, which simulates the virtual buses. All of this together we call the virtual vehicle. And again, this is can be whole set up with our COSIM, with our simulation middleware. And COSIM has several open interfaces, and you can connect additional software to it. I start at the top of this picture. Inca can be connected here, of course. Inca connection via XCP to the virtual controller, so that you can apply some calibration and diagnostic use cases on the virtual controller. Then you can, of course, automate this setup here, for example, with Tracetronics ECU test. And you can connect our CoSIM experimental environment and represent some measurements that show what's happening on this whole virtual vehicle. Also apply some changes there. So this would usually a user look at or a software tester look at. This all can run on a PC, on a virtual validation PC, which is a standard PC where our tools are running on. And this we would call one software in the loop setup. So no hardware is involved here, no hardware ECU, which is of course a big advantage, because then you move from the hard real-time area with the hardware ECU to an adaptive time area where you can massively accelerate the simulation, and then of course you get a lot of efficiency improvement in this software in the loop setup. Now you can also connect our CycurFUZZ product to this virtual network. You can apply this fuzzer to CAN, for example, and start your fuzz run on the virtual target. And when the fuzz runs are finished, then you get those fuzzing reports out of it. And with those fuzzing reports, you get a better understanding about your network and software robustness, and get an indication about bugs, maturity of your software, but also security vulnerabilities. And you can take those and replay them when you have a new fixed software version later on. So this is the setup on a PC, software in the loop setup. And what we recently worked on is the execution in the cloud. Here, the setup is basically the same, but what we did, the CycurFUZZ tool, we created a headless version of it, set up a command line interface and an API, Dockerized this whole setup, so this CoSIM virtual vehicle together with CycurFUZZ, and ship the container to our ETAS Cloud Services model simulator. And there, the big advantage is you have a lot of more computing power, usually very state-of-the-art computing power in the cloud. And you can scale by splitting the test cases. And with that, you can set up parallel fuzzing modes. And another very big advantage, of course, is you can automate that. For that, within ETAS, we have our own group that focuses on the so-called embedded dev cycle, and they offer solutions for pipeline automation. And this is then an important link to the DevSecOps topic and testing your software and security always on a button click, more or less, while it is in development, and not just at the end or close to the SOP. So this gives a lot of efficiency improvement and a direct feedback to your software developers. And of course, also here, you get the fuzzing reports out of it, and then you can adapt your software, fix the issues that you found, and rerun with the replay option of CycurFUZZ. Now I will come to the summary. So we as ETAS, we offer CycurFUZZ for software in the loop. This enables automation and scaling in the cloud. This provides efficient embedded software robustness testing with fuzzing to significantly reduce the legal risks and unwanted behavior. And it supports the mantra of DevSecOps, security, and functional capabilities are tested and built simultaneously. And if you have any questions regarding these solutions, I'm very much looking forward to get in contact with you, or you can also get in contact with our regional colleagues, and then we can follow up. Thank you so much. Looking forward to meet you